All right. So, welcome. My name is Pim. With me are Jarrod and Dan. We will introduce ourselves a little bit more later. And we wanted to share a little bit about how we are applying Spinnaker to the internal cluster management system at Google called Borg. It's a foray into something completely unrelated to Spinnaker, and then an advancement to Spinnaker itself. We'll talk about how we're using it for internal workloads. And at the end of it, there's a little slide that has a stick puppet saying, "Why should I care? You're just humble bragging about all the things you have at Google that we don't actually have externally." And then there's a pop quiz at the end. So we have this perennial balance between declarative systems, which the Kubernetes community would like to let you believe are awesome and solve all world problems, and imperative ones, which at least most users that I'm familiar with internally at Google prefer, because they can predict what's going to be the next step and visualize this rather than declaring this intent and magically seeing their system converge to it. It is my opinion that we actually need both. Strictly so, we will not be able to do one or the other. Combination of both, I think, is a winning concept. Then we have a little show and tell on declarative rollouts with a tool that is not Spinnaker against Kubernetes. Then we talk about sort of the Spinnaker imperative workflow systems that we apply internally at Google. And then hopefully show that we advanced the state of the art within Google from 2016 to now. So grab some mics, gents. I would like you to introduce yourself.
I'm Jarrod Todd. I work in Kirkland, Washington, just across the lake. I'm an SRE at Google. I work on Spinnaker, and I also, when I have spare time, work on Google's Canary Analysis Service.
I'm Dan. I'm a SWE software engineer on the Spinnaker team in New York. I work primarily on this, Spinnaker for Borg, and when I have spare time, I work on Kayenta, which is Spinnaker's Canary service.
All right, and I'm Pim. I hail from the Zurich office. I am an SRE there, working on sort of a reimagination of the Google internal production control plane called Production 2020. We're not here alone. We actually have quite an extended team. There's a bunch of countries we hang out with. Dan and his team in New York, Jarrod and his team in Seattle, but we have a sister team of that in Dublin as well. And then the system modeling team that I work on is split between Cambridge, which is Boston, not England, and Zurich. So the state of the art of Google production at the end of 2016, I think the TLDR is it was a complex space. As Google built their services initially, back in 2005 or 6, they each had their SRE teams that would go take problems and solve them, and so we ended up with a bunch of rollout tools and monitoring tools, capacity planning tools, emergency response tools, essentially one for each team, pretty much. Some would share, but there was a lot of diversity out there. And it was really cool to have that diversity because you can choose some really good patterns and winners and sort of converge on the stronger denizens in some problem space. And it was also very expensive because each team essentially had to roll their own and maintain their own. Particularly worth calling out, we are Borg-based. I think people in the industry chastise Google every now and again for not running on our own cloud. I would joke around and say actually we do, because Borg is our cloud. And it runs a bunch of services like Gmail and Maps and web search and whatnot, but it also runs our cloud offering. So we run our VMs in containers on Borg. However, I think GCP is advancing and the industry is advancing much faster than the Borg ecosystem are, and so it is a good idea for us to actually pay attention and converge with it, lest we have our beautiful little island called Borg and the other millions of people are using cloud providers natively. And it was very expensive for us to roll binaries out across our fleet. A lot of people spent time sort of tinkering with their rollout pipelines, refactoring their code, doing advancements of their local solutions. The incumbent one is called Sisyphus, which is that Greek dude who kept on pushing boulders up the hill to just see them roll back down again, and you have to start And it's kind of indicative of both the rollouts as well as maintaining the rollout systems. And we had sort of several bugs, as we always do, that were really hard to actually address and fix because we had thousands and thousands of these Sisyphus instances, hanging out in production. So we thought we would maybe fix that. One thing that I think everyone here would agree with or sort of feel is adopting Spinnaker gives us a lot of perks in terms of developer velocity. People will know it as they maybe work on a cloud project or a Google project, or we hire them. They may have some experience already, which is good because Google's internal tools are internal after all. It will take a lot of time to learn them. Even if you were to move between teams, anno 2015-16, you would essentially learn a new version of the rollout tool, even if it was based on Sisyphus. Multi-cloud, I don't think this is a sales, concept at all. We are multi-cloud within Google. We obviously have Kubernetes and GCE, and we have Borg. So it'd be nice for us to be able to use the same type of tooling across all of those. And it's pretty comprehensive. Compared to the internal sequencers that we have at Google, and we have quite a few. Specifically, I'm very in love with Orca and how you can bend it to your will to execute rather complex nested workflows. Most of the other ones we have internally are quite static. You tell it what to do and it will do exactly that thing, and if in the middle you decided you want to do something else, well, you're kind of out of luck. Also, there is growth. I think as Andy was saying this morning, the amount of committers has grown by 50% or so in the last year and a half. That's going to grow even further, and it's just a matter of time before these open source systems like, say, Kubernetes or Spinnaker will have more people, more eyes, and more keyboards attached to them and make more progress than I would even if I hired 100 people to work on the internal tool. So this sharing of code currently is more of a one-way street. We took code from the open source community, but we should also be able to make this a bidirectional path and give some back. So there's one thing that I wanted to obsess about because I have had year-long discussions with teams within Google around the philosophical differences between declarative rollout systems and imperative ones. Lots of folks will be in a religious church camp saying that you should absolutely use declarative because declarative is awesome. And then other people will say declarative sucks because I like to sort of determine the ordered steps that my workflow is going to take. My position and that of our team is we need both. So you may be able to do some things declaratively really nicely. You may be able to do some things imperatively. And so we're looking for a marriage of these two worlds so that they don't have to compete, but they can complement and complete each other. So in particular, some pro and con list around declarative and imperative workflows. I see them more, the imperative ones, as business logic, around compliance testing, ensuring that we have enough introspection on the direction that our rollouts are taking. And the declarative ones are kind of rather obviously, here's a script on what I want you to do. Please go ahead and do that, and don't bother me with the details on how you get there. Some person next door called Andrew gave me a really nice sort of mental analogy between these two. When you punch in an address on your GPS in your car, it gives you a route to that place, and you don't pay it no mind if it takes 101 or 280 in terms of the San Francisco Bay Area. You'll just trust it because it knows what it's doing. For some reason, we think that's perfectly normal, but then at the same token, we do not want to just declare we want this container to run. Please just run it somewhere, launch it over 280 or 101. No, it has to be 101 because it's really silly that people do not make the mental leap between trusting a GPS sat-nav and trusting a declarative rollout system. If you are in such a camp that doesn't trust it, this line here actually gives you a little bit of comfort because you can be fully imperative if you wish and determine each step along the way. And when you get more trust in the system, maybe offload some of the steps to a declarative engine, which is why I definitely think we would need both. I'm going to now foray into something completely foreign to all of you because we've never talked about it publicly before. and it is a declarative rollout engine that we use in Google production. I think you'll note there's a lot of parallels with Kubernetes, and that's fully unintentional. We started our system slightly before the Kubernetes team developed theirs, but for some reason or other, independently, we both came up with very similar models. We call it SMA internally. It stands for Systems Modeling and Actuation, which is essentially an intent database where you put the shape of your services in, called ProdSpec. ProdSpec has a data model language, and it has a storage system that you could compare with, say, a Kubernetes API server in etcd, where you put in a bunch of resources. And it has a controller stack that is constantly scanning production as well as the model and is reconciling production to look like what you intended. We have a couple of extra sort of tidbits that we accrued along the way. In particular, we have a thing called policy-based rollouts, which is essentially a policy engine that determines under which circumstances should actuation occur. As an example, you might think of a calendar that blocks off pushes between Friday and Monday. And so even if you had an intent change over the weekend, that policy would forbid it to go out. Or another such policy might be, hey, if I'm moving a cell around from one place to the other, I might want to bring up my new cell before I destroy my old one, lest I run out of capacity. Things like that you can model as well declaratively, and the engine takes it into account. So how is this intent then expressed? So we have three major sort of elements of this. One is a partition, the other is a view, and the third is an incarnation. And partitions are administrative domains, say they belong to a team or a service. Intents are views upon the data, and incarnations are snapshots of how your sources of truth would look like at a certain point in time. We use Piper internally at Google, and so ours are CL-based. You could easily replace that with, say, GitHub digests of a merge. Every time that happens, this system will create these resources within the incarnation, model them with references amongst themselves. This front end needs this back end, and this back end needs this quota, say. Or the other way around, this quota provides to this front end. Directionality is not very important. And this model is created by generators. So there's not people that are tinkering, with this model by hand. They typically run a generator based on their sources of truth in Piper or in Git, and they roll it into a complete snapshot of how production would look like at that point in time and put it in this incarnation. And it gives us some really nice properties. The incarnation is immutable, so it's not that we're working at head, say, as you would in a Kubernetes API server. We take snapshots of how the resources are supposed to look like at this point in time, and this is sort of a hermetic and immutable set of data, everything we need to build that service on Borg or other clouds at that point in time. It makes rollbacks really convenient. If you know that CL 1157 was golden and CL 1234 is not, you can simply tell Annealing, please advance to 1157. It will have everything it needs to build the service at that point in time. So one of these services may look like a Borg job, a front end that's talking to some back end. Both of those Borg jobs need Borg quota to run in our cloud provider. We may have a big table, which then in turn needs big table quota to run as well. These arrows are actually an important part of this system. It allows us to determine the order in which we have to actuate things if we have multiple changes in a model at any given time. So how does that actually work? Let us say that we take this intent that I just described and we compare it against production. We have a bunch of assets, resources that have a diff. Then we know the relationship between those resources, and we can compute a DAG on which we execute. In this case, the big table, the orange box, and the Borg quota are the things that have changed depth first in the DAG, and so we know how to make those changes go away. And then we rinse and repeat. This is relatively straightforward for a reconciliation engine, I guess. So next time we compare it to prod, that orange and red box are now good. They have been pushed and they are at the intended state, and so we see these two blue boxes and the green box left over. And because there is, again, this ordering and dependency mapping, we know that the bottom blue box would have to go next, bottom blue box being some back-end Borg job somewhere. So we go and push that and then rinse and repeat. So this is going to be a little XKCD stick puppet that's attempting science. And it models sort of the architecture of this reconciliation engine called Annealing. So the components involved here is users manipulate these sources of truth, essentially pull requests right on Git or Piper change lists to tell the system what they would like to have production look like. And they store these in Piper. And there's other sources of truth as well that live outside of Piper, but let's, for simplicity's sake, say Piper is the place where we store the production state at any given time. These are picked up by a generator which reads them and maps the dependencies between systems and emits a prod spec. And that's that little diagram that I showed earlier. So this diagram here is an incarnation at a certain point in time, which is fully hermetic and all the information we need to be able to build that entire service from scratch at that point in time. This is watched by an agent called Annealing. And Annealing is continuously running a diff between production and the state that is modeled in prod spec. So it does this first by calling for each type of resource an asset plugin. It knows how to handle resources of that type, say the Borg job or the big table, which exposes a diff semantic. If you've used Terraform, much like Terraform has a diff semantic to see the difference between what I want and what is actually in the runtime. If no diffs are found, that's fine. This asset is considered settled and stable, so we advance to maybe other assets that do have diffs. And in particular, if we see a set of diffs, then we'll ask a DAG solver to create an ordering of changes that we would like to now apply. So a solver's job is to give us that DAG. We might have multiple DAGs, normally only for relationships of dependencies, like I need this thing to exist, but you can also imagine version dependencies. I need this version to be at least X or at most Y, sort of like apt might do in package management. Solver assumes the responsibility of giving me the ordered DAG to execute. Then when we have all of these diffs that we want to get rid of, we are going to ask a policy server, hey, can I get rid of this diff right now? As I mentioned earlier, you may have a calendar plugin that avoids pushing over the weekend or maybe over a holiday or like Black Friday or something like that. Or you may have none at all, in which case Annealing will happily make this diff go away. By simply calling a push semantic on the asset plugin, we've now validated that this thing is ready to go, and so we're now going to actually actuate it by updating the production state in the cloud provider, in Borg or other types of resources. And then we have many of these asset plugins. Essentially, each resource type has one, and provided they give us the diff and the push semantic, we can add them to Annealing just fine. And before I switch to maybe a little video, I wanted to point out that Annealing itself has no interest or desire to inspect the payload of the resources that it is handling. What I mean with this is it doesn't look at what you're defining in your Borg job or in your Kubernetes deployment. It only looks at the relationship between them, and it operates its DAG and its policies exclusively on that little model in prod spec without having to do deep inspection of the resources. And that has a really positive benefit and also has some downsides. The downsides are obviously you can make a little bit better decisions if you were to introspect the asset payloads, the actual resource definitions. But the positive news is we can apply this thing to essentially any type of resource. So we thought maybe we would run one for Kubernetes. It was about 2,000 lines of code. 2 people spent maybe a week and a half writing it. Great. All right, so this was a modest introduction to like 4 years of engineering work with a bunch of people in the SMA team that shows, hey, we can actually do pushes against Kubernetes and perhaps also other clouds if we were to have these plugins that expose the push and diff semantic against some downstream API. However, as I mentioned before, I really don't think fully declarative is the right model for all types of changes, so we also call for an imperative workflow system that interacts with this thing. And last year at the Spinnaker conference, we were just about to decide that Spinnaker was that thing. We made the decision shortly after the one in Los Gatos, and then we started actually implementing all this code. So over to the people who did that, Dan and Jarrod.
Yeah, So as Pim said, like we realized the need for a imperative sequencer. Spinnaker seemed to fit that need nicely. So we set about the Spinnaker for Borg project. This slide shows you the stack of, how we do our deployment stack, basically. Our mission in all this project was to make configs and binary deployments safe, fast, easy, reliable across both Borg and GCP. That was a big selling point for us, was that Spinnaker, if we could get it to talk to Borg, could get us both any cloud we wanted that Spinnaker could talk to. Right now we are using Spinnaker. I'll let Dan talk about the modifications we made. It's mostly vanilla. I'll call it mostly vanilla. We've made some changes to it, obviously. We are using the Spinnaker UI native with some minor UI tweaks, but nothing major. This shows where Spinnaker fits in the stack. We have our production platforms, which anybody can use to define how they want to manage their deployments. Spinnaker is below that. Releases and rollouts is the team I work on. We manage releases and rollouts across all of Google. And then SMA below that, because SMA, as Pim just showed, does deployments really well. And then we have our clouds below that we can we have all our resources in. So this is talking more specifically about the technologies we're using in this stack. At the top here we have Spinnaker, our sequencer. It's imperative. It's do this, then this, as the ABC. To do that, we employ a couple of other services that we've written inside Google. One of them is called target selection. Another one's called rollout analysis. And then we have rollback capabilities through another system. And all Spinnaker controls the imperative steps. We push down declarative operations down to SMA. This allows us to bridge the gap between Spinnaker and our other declarative systems and the clouds they run on. A little bit about each of these. Target selection, kind of obviously named. Spinnaker gives it a set of things I want to do, and target selection, based on some configured policies, says you can do this one. And then Spinnaker does that one. And then when that's done, it says, okay, now I've done that one, I want to do these other ones. And based on the policies, target selection, okay, you can do that one. Again, all through SMA. Rollout analysis allows us to analyze each step. You could do it after the first canary stage. You could do it anywhere you want, really, in the pipeline. Typically, we use it after canary. Rollback, basically, we can roll back everything, like Pim said, as a unit because we're using SMA. Makes it nice for users to figure out how they can go backwards safely. And I'm going to turn it over to Dan to talk about specific implementation stuff.
Okay, great. So how does this actually work? So the red here are the modified Spinnaker components. Not all Spinnaker components are shown here. Green is a single sort of API layer between Spinnaker internal services, and the yellow are internal Google services. So in some cases, Spinnaker is just talking directly through a proxy to an ACL database, canary analysis, and target selection. Jarrod's going to be talking about target selection and canary analysis a little bit more in a second. But the interesting component here is the Kubernetes bridge, which Spinnaker uses to speak with SMA. So what is this Kubernetes bridge that we've implemented? So we have a Kubernetes compatible API with like custom resource definitions. That is like Kubernetes kinds that are Borg job, spanner database, target selection strategies, and then controllers that in turn actuate those resources. And there's a lot of benefits here. So Kubernetes tools just work. So kubectl, and of course Spinnaker. So this isn't exactly what we did because we've done a lot of work to make Borg jobs sort of native and first-class resources in Spinnaker. But as a first approximation, Spinnaker takes Kubernetes CRDs and applies read and write operations on them. And so you can build up sequencing, deployment rollouts of Kubernetes CRDs without writing any code. And so that's really a first approximation of what we did, and then we've made it more native over time.
You should leave this on. Target selection. So as I mentioned, target selection is the thing that controls what should happen next. This is an example of a target selection config. This actually lives in ProdSpec. This is comes from a source of truth. And so in this simple config, basically, you have filters and you have constraints, right? The filters filter out candidates, and the constraints are what they have to meet to be a viable answer. And the filters in this case are I don't want to go anywhere where I'm doing maintenance. I don't want to go anywhere that doesn't get any traffic. And I don't want to go anywhere where the cell is not getting or is currently paging someone, because it's probably not a good candidate for a canary. And again, this is very simple. It has to be getting at least 10% of my global traffic, right? This is the policy we use for doing our canary, our first push. So we want to make sure we get a somewhat representative canary for our first cell. And we only want one of them. And the constraint is we only want one cell to come back. When Spinnaker is calling target selection, it's getting the list of things that it wants to update, again, from ProdSpec. And given for a given pipeline, it knows these are the things that are affected by this pipeline. These are the things I want to do next, and target selection is given that list and responds appropriately. This process just repeats. It's not just for the canary step, right? We have a different target selection policy for the post-canary steps. And you can do, I want to do one cell at a time. I want to do a linear progression. I want to do exponential progression. You can configure target selection to return anything you'd like, basically. And that allows Spinnaker to declare the sequence of events while allowing the pushes to be declarative, which is a pretty nice marriage of the two concepts.
I think we haven't mentioned, anytime you hear cell substitute.
Yeah, sorry. My Borg concepts come in.
Yeah. So just to make this a little more concrete, so for Spinnaker for Borg, we don't use Spinnaker's native deploy step. We use something we call a dynamic deploy that uses target selection. So Spinnaker doesn't know until runtime which job it's going to be pushed, where it's going to be pushing them, and in what order and how quickly. So in practice, that looks like something like give me a canary cell, Spinnaker deploys in that cell, then does a canary analysis, and then comes back to target selection and says, what should I do next? And should I push the remaining of the cells or some of the cells? And then target selection tells Spinnaker which jobs and which cells to push in.
And as Dan mentioned, we have a stage that does canary analysis. Kayenta is the Spinnaker concept. This one is actually not Kayenta proper because the metrics that we use are not available to Spinnaker. And so this actually uses our internal canary analysis service that we've had for years at Google. But it's the same concept. If you use Kayenta or any kind of canary analysis, you're familiar with what this does. You give it one set of targets, which is your experiment, and another set of targets, which is your control. You may give it some custom metrics that you've defined that are specific to your application that define the health of your canary. You may not. Like canary analysis internally, we know a lot about the binaries. We can learn a lot about them, actually. And so we have a bunch of default checks that come for free, like crashes, right? We can detect for free without the user having to tell us that a crashing binary is bad, And so there are a bunch of other checks. Some serving errors is never a good thing, so that's automatically a default check. But a user might want to configure other things for their application. So when Spinnaker has done its canary push via target selection, it then calls canary analysis and says, I've pushed this cell, compare it to this other cell that's not pushed, and give me a verdict. And this graph is just an example of what a crash. This is obviously a bad push. The red line, the spiky line, if you have color blindness, the spiky line is the canary. It's bad. It's crashing. And canary analysis correctly failed this and said you shouldn't proceed. At which Spinnaker would have stopped and would have thrown an error saying canary analysis didn't pass for this pipeline.
So XKCD lady here is saying, that's great. You're humble bragging on all the stuff that you have at Google internally. That is obviously all not available to us at all. So why should I even care? Right? There is a succinct answer to this. We're actually interested in sharing this stuff a little bit more broadly. We talked today about Spinnaker and the internal Google Canary Analysis Service, which kind of sort of looks like Kayenta, but is a little bit different. CAS itself is not super inherent or specific to Google. We like to use it with Monarch, but it might also very well use other time series, stores, Datadog or Prometheus or Atlas or what have you. I think it's a pretty good canary analysis service in terms of fidelity. We have these dynamic stages, right, that we showed. I like them a lot because it means we don't have to actually tinker with the pipeline that much. The pipeline has a stage that says roll out to canary. And what to actually select to roll out to canary is done dynamically, even if the prospect were to add cells or remove cells. With cells, I mean clusters. Then we have SMA annealing, essentially this declarative engine that takes the model representation of intent and goes and wheels over production to get you there. We currently use ProdSpec internally with the proto-based approach, mostly because we started a long time ago. I'm working on a demo internally to change that to be Kubernetes CRDs instead, which would be really nice, I think, because it's more idiomatic for most cloud users. When I say Kubernetes there, I obviously mean the API machinery, not the cluster management stuff. So you might model Borg jobs in the Kubernetes API server just as well as you might model Kubernetes deployments in there. We have target selection, which is, I think, a really nice way to declare how you would like the rollout to look like, not the specific order of places where you would like it to go. And then we have that policy-based rollouts, which I didn't really talk about that much, but is this component that shows us under which conditions should we actually do the actuation. Even if we determine that you're next, should we be whacking this cluster now or maybe not? I guess that's kind of all what we had. I'm genuinely interested in this question. Do you care about this at all? I assume maybe you might, maybe you don't. We think it has a lot of merit, particularly between larger deployments of resources across many clusters or different types of cloud providers. And I would love it to be able to share more. I have a mini survey. It is 1 page, I swear, and all of the questions are optional. You may want to take a look at it. I'll narrate it as well. It's goo.gl, capital SJ, capital XLFV. It's a useful signal for me, so please all take your cell phones out and tweet this because I don't have Twitter, as we already established this morning.